Hello, today I would like to talk about my experience in the experiment 3, synthesis of local anesthetic lidocaine, both part 1 and part 2 with you guys. So in part 1, I first collected 246 microliters of 2,6-dimethyl aniline in the 25 milliliters of the reaction flask, and I add 2 milliliters of the glacial acetic acid as the solvent in it. Then I also measured 175 microliters of the chloroacetyl chloride, and so far we have collected all the starting materials. So before proceed to the next step, I would like to determine what is the limiting reagent. We have two starting reagents, as we can see, is 2,6-dimethyl aniline and the chloroacetyl chloride. And after calculation, I found the first one has a lower amount of the millimoles comparing to the 2.20 millimoles. So we can say the 2,6-dimethyl aniline is the limiting reagent. Then, in the step of heating the reaction mixture in a hot plate directly, I observed the reaction mixture start to crystallize gradually, and is the white precipitate crystallize out. Then I set up the vacuum filtration apparatus and collect the product N2,6-dimethylphenylchloroacetamide in part 1. And here's my calculation for the result data I got. As we know, since 2,6-dimethyl aniline as the starting material and the limiting reagent has the 1:1 ratio percent with the product N2,6-dimethylphenylchloroacetamide, we can say the theoretical yield in the millimoles of the product is 2.00 millimoles, the same as the starting reagent. Then we calculated out the theoretical yield in mass of the product was the 395 milligrams, so we would expect that we will have 395 milligrams as the product. But from the product what I got, I found that I actually have 405 milligrams product. But I can explain it because I measured the melting point range was between 138.4 to 140.1 degrees centigrade, which is lower than the theoretical melting point range, which is like 150 to 151 degrees centigrade. So we can say it's not pure because the impurities in it would bring down the melting point range. And here is the yield percent we calculated out. Here's the step, and we got 102.5%. And then in the part 2, we need to first calculate to measure 5.00 molar equivalent of diethylamine. So in other words, I should collect the amount of diethylamine in the ratio of 5:1 to the product I got in part 1. Here's the calculation. And here I would like to show you the volume of diethylamine I should collect step by step through this calculation. First of all, we get an actual yield of the product in millimoles was the 2.05, and we times it by 5 to get 10.25 millimoles. That was the millimoles of the diethylamine we should get. Then we got a mass of it through by applying the molar mass of it. Then we got a volume, which should be 1060 microliters. And in the part 2, during the refluxing for 90 minutes, I observed the white precipitate crystallize in the reaction mixture, which most likely are the diethyl ammonium chloride according to the textbook. After 90 minutes, I transfer the reaction mixture by the pipette away from the crystals to the clean culture tube. Then we need to proceed to the liquid extraction. So first of all, we add HCl into the culture tube. HCl, which is a very strong acid, it can protonate the lidocaine free base to a salt to make it dissolve into the aqueous bottom layer. So when talking about the bottom layer, we can see the bottom layer should be the aqueous layer and the top layer is the organic layer, since the aqueous layer should have the higher density than the organic layer. As a result, in this liquid extraction, we actually isolated the lidocaine hydrochloride as our product into the aqueous layer. Then we repeat the same step and combine the two bottom layers together. Then now we got an aqueous layer with the lidocaine hydrochloride. Then the next step is to add the base into it to deprotonate it to get our final product, lidocaine free base.